So, I'm making this video because basically I've been asked to, and a lot of people are asking the same questions. A lot of people want some background to what's going on. Now, I have to apologise really for two reasons. The first reason is there is at least three good and competing models out there for what is going on. And this really is just my take. It's kind of a guide that I use when thinking about these processes. And it's almost bound to be wrong. It's just a guide, it's just my take. There are other guides, other ways of looking at it, and you know, if you look at this and you think that's a load of rubbish, by all means put one up yourself explaining it better. I have no problem with that at all. It really is just my take, so I have to apologise for that. If it comes across as being the word of law, it's not meant to be. It's really just meant to be a guidance and explanation. The second one is I don't really know who it is that I'm talking to, so it's quite difficult to pitch the level correctly, because I get a lot of correspondence from people who are pretty aware when it comes to chemistry, and they're pretty good. And I get some from, well, guys who are just starting out on that road and don't really know that much and have a fair bit to learn. So I don't want to be patronising to guys who know a lot. I don't want to be insulting to guys who don't know so much. So it makes it difficult for me to pitch it. So I'm going to try and pitch it at a level that I think is going to help. And if I get it wrong again, I'm sorry for that. Okay? So, well, I think we all know what graphene actually is. And graphene is a planar arrangement of hexagonally bonded carbon atoms, pretty similar to a beehive honeycomb. The carbon atoms have a propensity for arranging themselves in hexagonal rings, and that's because it's the lowest energy state, and they are quite happy in that state, and they rest there quite nicely. Now, you do get problems with that. You do get 5 carbons and 7 carbons in the ring, but predominantly it's a 6-carbon ring, and predominantly they lay themselves out in one flat plane. Now, that is graphene, and when you think about graphene, that's what you're thinking about. Now, there's some confusion over what is graphene, what is graphite. Graphite is stacks of graphene. So the graphene is a naturally occurring material. The graphite is stacks of it that we're aware of and that we come across and is in our pencils. Now, the layout of the graphene sheet is what gives it its unusual properties, in that because it is bonded in a long sheet and because of the way carbon atoms bond, then there is a cloud of electrons above and below the sheet that allow the movement, again this is just a way of putting it, that allow the movement of the charge along the sheet really, really easily. Now, the direction perpendicular to the sheet is the c-axis, and that direction doesn't allow charge to move particularly well. So graphene conducts extremely well along the plane, and quite badly actually along the c-axis. It also means that because it's atomically bonded in the plane, it's incredibly strong in the plane, and because there isn't that much in the way of bonding, in fact there's nothing really in the way of bonding between the planes, it's actually very weak between the planes. Now, these are relative terms, strong and weak. But it's what gives graphite its particular property, is that when you rub graphite, it will cleave along the plane really, really easily, and that's used as part of its property as a pencil. That's why it writes as a pencil. It cleaves easily, and so you can slice off sheets of this stuff, and it lays on the paper. Now, there are forces that hold those sheets together, and you can think of it as a kind of a ream of paper, if you like. And if you make that paper static, and you lay one sheet on the other, the two sheets will hold themselves together, and to pull them apart actually takes a bit of force. Now, all forces are related by the square of the distance, as I'm sure we all know, and at an atomic level, of course, the distance is quite small. So that inter-sheet attractive force is by no means inconsiderable, and although we refer to it as a weak force, because in atomic terms it is, it's actually relatively, for us to overcome, a strong force. Now, that force is called the van der Waals force. So what we have is a whole arrangement of single planar sheets, stacked on top of each other and held together by a van der Waals force, an intermolecular force that, a bit like static electricity, sucks the sheets together and makes them difficult to separate. Now, they can be separated, and you can do that just by drawing with a pencil. That will separate them out, but that will separate them out in relatively thick chunks. And when we're talking about thick chunks, we're talking about sort of 50 to 100 layers being separated off, being cleaved off. That's quite thick in the terms that we're looking at. Another way of doing it, and researchers are doing it, is to take a lump of graphite, stick it in a sonic bath, whack on the sonic power, and shake them apart. That's all ultrasound really does, is shake things very, very quickly. I mean, there is a setup of what they call cavitation, that is, small microbubbles form in the fluid, and there's a high pressure, high temperature in those bubbles. When those bubbles collapse, they collapse with an explosive force which shoots the graphene sheets apart. And there is one paper that I've read where a guy does exactly that. Now, the main problem is it also shatters the graphene sheet up, so you don't get lovely big old sheets of graphene. What you get is lots of tiny little particles of graphene all shattered up and mixed in your water. But it does it, and you can mechanically separate those sheets out into graphene. And that's what everybody is after, is the graphene. Okay, so pay attention to that particularly. It's the graphene that you're after. That's where you're heading for. Okay, the graphene oxide stuff is just a way of getting there. You're really heading towards the graphene. Now, what we're looking at doing when we're trying to get the graphene is to cleave those sheets apart. Now, cleaving the sheets apart actually has a lot of strategies. There's a lot of ways you can actually go around doing this. And if you read the research papers, there's an awful lot of ways that people are doing it. Now, one of the main motivations for me beginning this series was I was reading one of the forums, and I think it was over Unity. And there was some guy on there, and he was a forum guru. A forum guru is just one of those guys who knows everything. And he said quite categorically, if you want to make graphene, you have to have a big and expensive lab. Now, I kind of take exception to that. I don't think that's true in the least. I think anybody with half an ounce of brain, a bit of persistence and a willingness to experiment can actually make graphene in their own home. So my main motivation has been to come up with the method not to make graphene, but to make graphene in your home with materials that you can get hold of, not strange exotic materials that you have to order or have a license for or have to be a big lab to get, but just things that you can get hold of at the do-yourself store over the internet with equipment that can be got in the average home. So that's what I'm trying to do, is make graphene that way. And in order to do that, then we have to think about the processes that are adaptable to that. Now, graphene, as I say, can be made from graphite by essentially sticking a wedge between those sheets of graphene and forcing it apart so that it's apart far enough that the van der Waals forces have been weakened enough that other methods can be used to shake it apart. And the other methods are things like ultrasound sonication in a jeweler's cleaner. That's one way of doing it. There aren't that many actually, and that's really the one that I've come up with. I suspect ball milling would do it. A blender probably would do it, but you're going to damage the graphene that way. Sonication's my preferred one. Or to come up with a process that completely obviates that, so it literally splits it apart into single sheets that are already there, ready for you in solution that you can use. Now, in order to do that, separate those pieces apart, then the standard approach has been and still is to create graphite oxide. Now, graphite oxide is different to graphene oxide in the same way that graphene is different to graphite. Graphite oxide, or graphitic acid, is what Hummer first called it, incidentally. Graphite oxide is the oxidized form of graphite. And when you split that apart into single layers of graphite oxide, it becomes graphene oxide. The reason you're making graphite oxide is that obviously those sheets don't extend to infinity. Those sheets of graphene stop, and at the ends there they have functionality. They're usually terminated by hydrogen bonds, but there are other bonds that you can find there. You can find hydroxyl bonds, carboxyl groups, carboxyl groups, hydroxyl groups. You can find lots of different things sticking on the ends there. When you oxidize it, what you do is add groups on there, and those groups are bigger than the original hydrogen bonds, and because they're bigger, it forces the plates apart. Now, it doesn't force the plates all the way apart. What it does is forces the edges apart, like that. Okay? But then once you've forced the edges apart, you can get something into that gap, and that's what we're trying to do. Now, part of the oxidizing of graphite and splitting it up in the Hummers method is to add functional groups onto the end to separate it out, as you said, and then to put a wedge in, and that wedge is called an intercalation compound. Now, there are lots and lots of intercalation compounds, but the one that Hummers used is the sulfate, and that sulfuric acid, high concentration of that high concentration of sulfuric acid is in fact intercalating into the gaps of the graphite. Once the graphite has been separated out to graphene sheets, oxidizing the ends of it, then the sulfate is forced in to there. And that's what the sulfuric acid does in there. Okay, so the oxidizing agent adds functional groups to the edges of the graphene sheet. The sulfuric acid is an intercalation agent that's forced in between the graphene sheets, and that acts to, first of all, do that to the graphene, and then do that to the graphene, force the sheets apart, and thereby weakening the van der Waals forces. And that's what we've done when we've used Hummers' method on a piece of graphite. Now, you don't only have to intercalate with sulfuric acid, you can intercalate with lots and lots of things. And that's how graphene intercalation compounds are formed. Now, if you have a graphene layer, the intercalation layer, so sulfate or ferric chloride, we've done ferric chloride as well, and then another graphene, another sulfate, another graphene, so that between each layer of graphene you have a layer of intercalatant. That's called a stage 1 graphene intercalation compound. If you have 2 layers of graphene and then a layer of intercalation, 2 layers of graphene, that's a stage 2. Stage 3 is what you would imagine it would be, and so is a 4, and so is a 5. So, if you can make everything as a stage 1 intercalation compound, in theory, you should get nothing but single layer sheets. Now, of course, nothing happens in theory as it does in practice. And when you come to separating those sheets out, then some of it goes back into solution. So you get a mixture of stage 1, 2, 3, 4, 5, and you get a whole mixture in there of your sheets. So nothing actually goes according to plan, unfortunately. So that's what we're doing when we're doing the Hummers method. Now, when you add the hydrogen peroxide, what you're essentially doing is an explosive reaction. And you're using the hydrogen peroxide as an agent to explode the intercalation compound and really force it apart to help break it into single sheets. And again, everybody gets hung up, incidentally, on graphene oxide, and there's no real reason to be hung up on graphene oxide. You have to think about what it is you're actually trying to do. Nobody wants graphene oxide, it's a pain in the neck, because at the end of the day you have to reduce the graphene oxide back to graphene. So it's only done because it makes it easier to handle it. So if you can come up with a method where you don't have to produce graphene oxide, you're going to save an awful lot of time and trouble if you can produce the graphene directly. And there are lots of methods out there to do it, and none of them I've actually looked at, particularly, well, outside of my job anyway. None of them I've actually looked at with this home experiment, because I think they're just beyond what we can do with the home equipment. There's a really good one called BottomUp, where they use a plasma needle actually, and an ionic solution with the graphene dissolved in it, and you put a current through that solution using the plasma as an electrode, and you can electrochemically separate the graphene out very nicely indeed. But it's a laboratory way of doing it. It's not a home way of doing it, and it's not an industrial way of doing it, so I haven't even looked at that. But it's there. There are a couple of other really interesting things that I've come across recently, in fact. that I'm sort of working on at the moment. And one of those is to take a ferric chloride graphite intercalated compound and drop it in hydrogen peroxide, because ferric chloride, of course, undergoes a Fe3Fe2 reaction, which is exothermic and relatively violent. So if you have an Fe3 intercalated graphite compound, so FeCl3, and you add hydrogen peroxide to it, it'll go to FeCl2 and give out a lot of heat and energy. And that can be used to force apart the graphite flakes to make graphene. You can also do the intercalation process a couple of times. So on the first time, maybe you get a stage 5 compound and you break it up so you've got 10, 20 sheets in layers. You run it again on the exfoliated graphite intercalation compound that you've just done, you'll get something at 1 and 2 layers. And I'm also looking at a process that uses environmentally friendly materials, actually acetic acid and hydrogen peroxide, on a double and triple intercalation route that will give you nothing but single layer graphene particles in solution. None of this tedious mucking around with graphene oxide, and you're left only with a solution of reduced graphene that you can literally paint on a surface. Now, other methods of making graphene are what are called a bottom-up approach. We're using a top-down approach. That is, we're taking a bulk material and attempting to break it up. A bottom-up approach takes the elementary materials and tries to build the structure directly. And that's what chemical vapor deposition is all about. It uses a carbon source where you create a carbon gas, pass that gas over a copper film, and the reason you pass it over copper is because when copper is heated, it absorbs the carbon. When you cool it, it gives it back out again, but it gives it back out again in the hexagonal crystal structure. And that's being looked at quite intensively as a way of making single sheet graphene. Now it looks very promising, and there are research papers showing how they've made 30-inch squares of this stuff and claim it to be a single sheet. Now if it is a single sheet, it'll actually be rubbish, because if you think about it, then if you have a big old square of copper and you start to cool it, it's not going to form a sheet as one go, it's going to form in spots. And as these spots grow together, they're going to grow together at a mishmash. So one will be growing in that direction with that grain to it, the other will be growing in that direction with that grain to it, and they won't quite meet up. And because they don't quite meet up, at these crystal joins here, you're going to have poor conductivity and weakness. Although the graphene is strong when it's a single sheet, at the joins it's actually quite weak. So when you stretch or deform that, or heat it and cool it so it deforms itself, it will crack along those joints and you lose conductivity altogether. So having a single sheet of graphene may seem like an ideal, but it isn't. It can be an absolute pain. What you actually want is 2 or 3 sheets laying over each other that interlock so that you can get some bridging. Now obviously the problem with graphene is it doesn't conduct very well along the c-axis. So what they're doing is mixing the graphene with carbon nanotubules. Now all of this stuff is really beside the point. It's just to give you a flavour of what is actually going on. What I really want to get across here is that what we're trying to do is a home method of doing it, a way that can be reproduced by the average inventor, the average experimenter. We're looking at something that is environmentally friendly, something that doesn't cost an awful lot, something that's relatively simple to do, and something that will give us an end product that we can actually manage. Because another problem with the graphene oxide is the end product itself is actually quite difficult to manage. So let's go back to the Hummers method and have a think about that again. And the Hummers method, remember, what we're doing is we're attaching functional groups to the end of the graphene sheets to force the graphene sheets apart. Then we're passing an intercalation agent into there. So we're oxidizing the end of the graphene sheets with potassium permanganate, using the sulfate as an intercalation agent. The reason the nitric acid or the phosphoric acid are there is, I think, that they act as catalysts. The nitric acid is another oxidizing agent, incidentally. But I think they have a catalytic action too, to a degree. So it helps force that intercalation agent in there. Then we terminate that process by rapidly oxidizing it using H2O2, hydrogen peroxide, which explosively forces the plates apart, and we get exploded apart plates of graphene oxide. And when you do the process, what you find is that your solution turns from a relatively loose liquid into a kind of gelatinous mess. When it goes that yellow colour, when you've added your hydrogen peroxide and it goes the yellow, it's quite jelly-like and quite difficult to manipulate when the washing process and the drying process are really time-consuming. They take an awful lot of effort to do, because the mixture that you get is difficult to filter. It's difficult to filter because it's quite gelatinous. You wash it with deionized water, incidentally, to wash out any of the salts left over. You wash it with hydrochloric acid to get rid of any contaminant metal ions that you've got in there, or any of the excess sulfates or other bits and pieces that are going to be floating around. There's a fair amount of rubbish created in this reaction that sits on the graphene, and the hydrochloric acid water washes it to try and get rid of that stuff and leave you with a purer product. But the washing processes are incredibly tedious to do. So I've been looking at improving those methods, because although the production of graphene oxide only really takes about 10 minutes of your involvement time, the washing takes days, and it really is tedious. So I've been looking at ways of creating the graphene directly without all these intermediate washing steps, and then without having to reduce the graphene oxide. Because once you produce the graphene oxide and you want to laser scribe it, then obviously what you need to do is clean it, paint it on there, scribe it to get it back to graphene to make it conductive again. So that's the kind of things that we're up to, and the sort of things that we're heading towards and looking towards doing. Now, I have actually made the graphene oxide and laser scribe disc. The reason I didn't bother putting it up is Eric Goecken has a really good demonstration video on how to go around doing that, so why bother repeating it? Just have a look at his. It's the same process. And I've burnt it, and I've got a couple of supercapacitors ready to go. I'm finishing off the other supercapacitor, and I'm going to do a video of all of the supercapacitors together. I'm not particularly happy with the graphene oxide because, as I say, the process of washing it is really a drag, and I think that can be improved. I think also that people get too much caught up with graphene and this wonderful material that it is. I mean, it is a wonderful material. There are tons of really interesting things you can do with it, and it certainly does a good job on supercapacitors and transparent electronics. But it's not the complete story. There's more to supercapacitors than the conductivity of the graphene, much more to it. And so some of the stuff that I've been doing has been looking at the structure of the electrodes of supercapacitors, which is why I've been going into chitin and talking about nitrogen-doped carbon. Okay, so I hope all this, I know it's been a long one, but I hope it's actually been helpful to you. And if you have any questions, really, by all means ask. I'll try and answer them. And hopefully it's made some sense. Anyway, thank you very much, and I hope that helps.